Hi everyone. Let's start today's Silicon Valley machine learning meetup. We hold this kind of meetup every week. So if you have anything to say to this crowd, come see me. We can arrange another meetup like this. And this here is HackerDojo. This is a member-run community. So if you like this kind of place, please come see anyone at the front desk. They will give you a tour and show you what this place is about. And there is another hackathon going on this weekend at Nest GSV. It's a big data hackathon, so if any of you guys are interested, you should look up Data Hack 14, and all the description should be out there. Any of you guys have any announcements you want to make? Okay. So Eugene is a senior software engineer at the data processing and analytics team at Google, and he's building distributed frameworks such as MapReduce and Flume. And he also worked at Yandex and Variance before this. So and he's going to talk about global sensitivity analysis.
Thanks for introducing me. So yeah, indeed, my name is Eugene. I work at Google, the distributed data processing frameworks team. Specifically, if you've been watching Google I/O, I'm on the cloud data flow team. And MapReduce, as you probably know, is actually deprecated. All right, so I'm going to talk about something entirely different today. My motivation for learning it was related to my job. I was basically looking at the performance data of MapReduce jobs at Google. I was analyzing the data sets that said basically what the parameters were in each of the, let's say, many millions of MapReduces from every month at Google, so what the parameters were and how long they took and so on. And it bugged me that I didn't know nearly enough statistics to understand what was going on there, because these parameters interact in all kinds of interesting ways. And there's literally hundreds of them, starting from simple things like number of machines or size of input, to the more interesting ones like type of input or the data center where you're running, or the kind of computation you're doing. So basically my parameter for classes and so on. So I'm going to disappoint you. I didn't manage to do anything interesting with this with that data because my priorities shifted, but I think I nevertheless learned a lot of interesting stuff, and I'd like to share it with you. Maybe you will find a better application for it than I did. So during my inquiries, I discovered that there is an area of statistics called global sensitivity analysis. It is tasked specifically with trying to figure out what's going on in a model that has a ton of parameters that possibly interact in unknown ways. And individual analysis of dependence on each parameter gets you nowhere. Because, for example, when you look at the scatter plot of the response versus just a single parameter, you just get a cloud of points and it tells you nothing. So there's going to be a better way to look at the dependence on multiple parameters. Turns out there is a branch of statistics that deals specifically with this. It's called global sensitivity analysis, and there is an awesome book about it. It's actually the only textbook on this topic that I know, but it's really good. So I read it and I liked it so much that I basically made a presentation that summarizes what the authors tell there. The authors are statisticians. I think they work for some like intergovernmental research panels, and they use these techniques to analyze like worldwide economic models or industrial processes and things like that. So it's practical. So as I said, the problem statement in global sensitivity analysis is which parameters matter for some definition of matter, and what exactly is that definition is an interesting question that will occupy a big chunk of our time. The simplest way to talk about which parameters matter is when you have just a single point where all parameters are fixed and you're wondering how much the output will change if you just nudge one of these parameters a little bit. That's called local sensitivity analysis. There is not very much to say about it as far as I know. You can just like compute derivatives of your model with respect to it. If you have the model as a function that you can compute, you can just compute it around this point and compute the derivative. If you have some existing data set, then you can, again, just look at nearby points. But the point is that local sensitivity analysis talks about the neighborhood of a single point. But it doesn't tell you anything about the behavior of the model or the function over the whole input space. And this is what local sensitivity analysis is about. So basically, it tries to quantify the importance of certain parameters or parameter combinations. It explicitly does not task itself with figuring out what exactly is the character of the dependency on certain parameters. It only tries to quantify which parameters are dependent and which aren't. So the techniques that we'll talk about are very important. For example, if you have a search relevance formula. I'm just talking out of my head. I have no idea how Google search relevance actually works. But I imagine that if I was building a search engine and if I had a formula with, for example, 1,000 factors that I invented, I would be interested in which of these factors are actually making a difference. So I could probably apply some of the techniques that we'll talk about to see which factors matter for the output of my formula. There is a bunch of applications, there's a bunch of classes of problems that look something like what we just talked about. So one is called factor prioritization. It's when we have a model of a lot of factors and we try to determine which factors are the most important in determining the output. This probably means that we can approximate the model by looking at just those factors. And this also means that if we would like to make the output of the model more certain, then this is the factors we should be making more certain. This is the setting of risk analysis and variance cutting, the third setting over here. So if you have a model that depends on a lot of uncertain things, and you have to make some trade-offs with respect to which of them you want to measure more certainly, you have to do sensitivity analysis. For example, if you're an, insurance company, and you have some risk models that tell you what's the risk that someone will, break their car in the next year, and you can compute these risks based on some things that you know about the person, but you don't know them for certain, but you have limited resources for more detailed research. So sensitivity analysis can help you understand which factors you should be focusing on, which factors will give you the best reduction in uncertainty of your result. And one last setting is a particular case of this where the output is binary. So, for example, you have an industrial process that either goes well under some conditions or it doesn't go well and it diverges or explodes or just produces not what you would like it to. So if the output is binary, you may be interested in which factors are the most important for determining if you'll have a good or bad output. This is kind of just a case of the applications above, but it's an interesting one. It's called factor mapping. So we've described the settings. Now let's see what in particular we'll be talking about. So first we'll talk somewhat about model decomposition. This is the problem where we are trying to simplify a complex model by decomposing it into simpler parts. For example, if we can decompose a model as a sum of two models which depend each on just one factor, then we can analyze the dependence on those factors individually. Then we're going to talk about experimental design techniques. And the reason we're going to talk about them is that these techniques are designed to allow us to extract the most amount of information from the fewest number of data points. And naturally, this is important when we're dealing with models that are expensive to evaluate. This can apply both if this model is a function that is just expensive to compute, or this can apply if the model is a natural process that you can afford to observe only a certain number of times. So you cannot afford to do like experiments on a country's economy model with 1,000 values of the parameter, because no one's going to let you do that many experiments on real people. So experiment design matters because it allows you to extract a lot of information from a small number of points, especially in cases where you have a lot of parameters. So the trivial ways to choose which points to look at will yield an exponential number of points to look at, which is unacceptable. And alongside experiment design, we'll also talk about how to find influential factors extremely quickly. This will be like one of the most amazing things that I learned from this book. It turns out that, for example, if you have a model with 1,000 parameters, you don't even need 1,000 measurements to throw away the unimportant ones. You can do with fewer than 1,000. How exactly that is done? Stay tuned. Then we'll talk about the elementary effects method, which is one particular method for quantifying the sensitivity with respect to a single parameter. Then the main part of the talk is variance-based methods. We're concerned with taking the variance of the output, basically looking at how much the output varies with respect to its mean value, and trying to decompose that variance into parts attributable to different factors. So, for example, we can say that factor A explains 30% of variance, and factor B explains 10% of variance, and the interaction of factors B and C explains another 50. And we'll also talk about how to summarize the influence of a factor in the output variance. And finally, we'll just talk about what applications in practice this can have, specifically for, I imagine, someone like Google, in my opinion, and some questions that are not discussed in the book, but I think are very important, and I have no answers to. All right, so the first thing is decomposing models. Decomposing models is important because if we can decompose the model, we can decompose the sensitivity, and in general, the parts are easier to analyze and reason about. Some models are really easy to decompose, so if a model is just the sum of terms that depend on a single factor, then, well, there is not much more to say than about sensitivity analysis. We can explicitly say how does the sensitivity of the model with respect to a factor look like. We just look at the function fi. And for example, if it's usually not that big compared to other functions, then we can say that the model is not very sensitive to this parameter. Not all models are additive. Some models can be made additive though. So for example, multiplicative models can be made additive if you just take the logarithm of those. This is important, I think, for example, if we're analyzing something like performance of data processing jobs. So I imagine it's probably multiplicative with respect to number of machines and input size and so on, rather than additive. And I imagine that just taking the logarithm of many parameters would help greatly in making the model additive and making it simpler to analyze. Well, some models are neither. Some models are actually more complex and have complicated interactions between terms, but we still need to find some way to tell how sensitive is this thing to x2. We cannot extract a specific term that relates to just x2 because the influence of x2 depends on what the value of x3 is. So we are going to have to account interactions explicitly. We'll talk about that. So it turns out that there is an extremely powerful technique for model decomposition invented by the Russian mathematician Ilya Sobolev. He's actually still alive. I think it was invented somewhere in the middle of the 20th century. So it's called high-dimensional model representation, and the point is that we're decomposing the model in an additive way, but to terms attributable to increasingly bigger subsets of the inputs. So there is a constant term, and there are terms attributable to each individual factor, and then there are terms attributable to pairs of factors and 3 tuples of factors and so on. This kind of decomposition has an interesting property. So if we require that all of these terms have 0 mean, except the constant term, then it is unique. Another interesting property that actually makes it practical is that if the model is even remotely additive, then higher order terms will be really small. So for example, there are some methods for classification that only look at factors and combinations of 2 factors, and these methods work remarkably well because many models that we're trying to approximate using machine learning have really small, higher than 2 order terms. So this is what a high-dimensional model representation is about. It's about decomposing the model into a sum of terms attributable to subsets of factors in the hope that large subsets won't matter. So that most of the interactions will be possible to describe in terms of single factors and pairs of them. Here's how we can compute this decomposition. So the constant factor term is just the mean value of the output. The term attributable to a single factor is the conditional expectation on that factor, well, normalized to 0 by the constant term. And well, the still higher order terms are also similar. Basically, we take the conditional expectation on that combination and we normalize it to 0 mean. So take a pause and think about what exactly that means. That means that if you have a complicated model, for example, if you have a model with, I don't know, 20 factors, you have a million data points with these 20 factors, and you can decompose this model into first a single number, which is the mean value of the output. Second, you can get 20 scatter plots of this model against each individual of these 20 factors. These are terms of the model that account specifically for its dependence on these 20 factors. And you have like 400 second order scatter plots. But the point is that you're decomposing the model into a number of simpler dependencies. And the first order dependencies actually look like simple scatter plots, and they will tell you a lot. This decomposition will be extremely important later on because we'll see that it applies not just to the model itself, but also to its variance in a really interesting way. Yeah. So another thing about it is that if you have decomposed the model into such a representation, then if the higher order terms are small, you can throw them away, and basically you can approximate the model by just taking a sum of the lower order terms. And here's what that gives you. You can approximate those functions using regression or splines or something else. And for example, it may take me 1,000 model executions to compute those approximations and to get some approximations of these functions fi and fij. But after you did those 1,000 executions, you can use those approximate functions instead of the original model without ever running it again. So you can run a million more experiments that analyze something else about the model without actually having to run the model and just looking at the approximation of its decomposition terms. Well, there are obviously some limits to that, but you get the idea. So this technique is called meta-modeling, where we're approximating a model and using the approximation for further analysis of the original model. Yeah, remember this. As I said, it will be really important. Okay, now it's time has come to talk about experiment design. So for much of the rest of the talk, we'll be talking about how to extract a lot of information from a small number of data points. And this has 2 parts. Part 1 is how to choose the points, and part 2 is how to extract information from them. Experiment design is about how to choose the points. We have to choose few points because, well, that's what we're trying to achieve. We're trying to avoid having to do a lot of expensive experiments. We also have to sample the input space in a representative way or in a fair way. So it's actually two separate notions. So we have to sample the input space in a way that all important regions of the input are covered. And we also have to make sure that all possible inputs have the same chance of being chosen. Otherwise, we may just ignore some inputs that may turn out to have been important, but we just didn't look at them in experiment design and didn't even have a chance of looking at them. So there's a really simple class of experiment designs called one at a time. The point is that we have a number of data points where two neighboring data points only differ by the value of a single parameter. So on the right, you see a really simple one-at-a-time design with 3 points for 2 parameters. And the advantage of this kind of designs is that if you have a pair of points that only differ by 1 parameter, then whatever differs in the results of these points, you can safely assume that it's because you changed that particular parameter. Now there's also uncertainty and noise, but that's a separate matter. And the point is that other parameters are not guilty in the change in the result. And these kinds of designs are really easy to produce, obviously. So the problem with them is, the problem with this is, of course, first that you get only 2 points per parameter, though you can fix that if you just take more neighboring pairs. And the other problem is that you're using a lot of points. You're using number of parameters times number of points per parameter, something on that order of magnitude. And that can be a lot if you have a lot of parameters or if you would like to cover the range of each parameter finally. So the question arises, can we do better? Of course we can, otherwise I wouldn't be giving this talk. And here's an idea of how to approach that. So suppose you have 2 parameters, x and y, and you would like to explore 3 values of x and 3 values of y. One way to do it is to draw this kind of triangle. So if you choose just 3 points like this and you project them on x and y, then it turns out that you have explored 3 values of x and 3 values of y. The problem is that you no longer have pairs of points that only differ by 1 coordinate. So the influences of x and y are mixed. Maybe there is a way to mix this influence, and then we're good. And obviously there is, and that's what we'll talk about later. So this is the goal. How do we place points to get a lot of information about many parameters at once? Let us see if we can approach this by just taking a bunch of random points and hoping it will be good enough. Here's an exercise. So here's two sets of 2-dimensional points thrown into the square 1 by 1. And I'd like to ask 2 questions. One is which of these looks more random, and the other is which will be used to do statistical estimates. Both of them have 100 points. Yeah. Okay, so which one do you think is random? Who thinks it's the one on the left? Okay, who thinks the random one is the one on the right?
Yeah.
Cool. So the random one is the one on the left.
On the left?
Yeah. Randomness does not mean uniformity. It only means that it's not predictable and that it's uniform in the limit. The one on the right has been explicitly made more uniform than it would be if it is chosen just randomly. On the right, we have split the square 1 by 1 into 100 squares and placed the point randomly into each one of them. So we got a result where every point on the square has the same chance of being chosen, and every region of the input space is covered. But we also achieved a goal that every region, each one of these 100 regions is actually guaranteed to be covered, unlike the completely random sampling. So random sampling suffers from these accidental clusters and gaps. So we have something like a cluster of points over here, and we have a gap over here. So it's not predictable, it's random, and if we like took maybe 100 more points, maybe these gaps would disappear, but there's also some chance that they wouldn't. So that's the problem with just simple random sampling. This technique is called stratified sampling, and it's actually a more generic concept. So the problem with random samples is that they have clusters and gaps, so we have regions that are over and underexplored. And if we try to, for example, compute the mean of the output using a random sample, we'll get something like inverse square root of accuracy, which is not really good. So to get 10 times more accurate, you need 100 times more points. And another problem is that if you actually looked at the data that you sampled, which, well, you're already a good person if you do that as opposed to just trusting the analysis. But if you looked at the data and found that you have a gap in the data, what are you going to do with the random sample? Are you going to just sample more points and hope that they somehow fill in that gap? There was a question for you back.
I'm actually wanted to I think the word random that you're using here has the same problem of the uniform. We're assuming when we are using random sampling, we are going to uniformly randomly sample the data. That's why we fall into gaps. But if you consider the distribution given the data, then there is a more chance to sample the data from the cluster rather than the gaps. Then having the gaps doesn't have the problem. But if you're assuming random sampling, going to uniformly sample the data, and if your data is not uniform, then of course you fall in the gaps.
Yes, that's a good point. So if I understood the question correctly, it is that if the distribution of the data you're trying to model is actually not uniform, then probably it is supposed to have these gaps. Yes, of course it is, but so modeling non-uniform distributions is a separate topic, and for now we're just talking about modeling uniform ones, because the non-uniform ones can be reduced to them in a way that we'll discuss later. And, well, the gaps here were not because the distribution of the data is not uniform. And if you have data that actually is supposed to be non-uniform, well, maybe a random sampling would have produced an accidental cluster in a place where there's not supposed to be a cluster. Or it would have produced a gap in a place where there's not supposed to be a gap. So the problems of random sampling producing clusters and gaps are not specific to attempting to do uniform sampling. The point is to do representative sampling. And random sampling gives you really poor guarantees of being representative. So there is a high chance that you won't cover some regions that you have to, or that you will overcover regions that you don't want to. So that's what stratified sampling is about. Stratified sampling is about explicitly and deliberately sampling in the regions that you know have to be covered, and sampling according to how much has to be covered there. So, yeah, the final problem I pointed out here was that with random sampling, you have no guarantee that you will actually correct yourself soon enough. So you'll correct yourself with a conversion speed of square root of n, which is not very good. So stratified sampling is a strategy where we would like to be sure that we cover a certain set of regions of the input data. We just sample within those regions as opposed to sampling the whole input and hoping that these regions, that we also sampled something in those regions. In the example before, we looked at where the regions were parts of the 1 by 1 square, but it is also widely used in just survey design, in sociology and so on, where we can stratify by gender or nationality or geographic location and so on. So if we really would like to make sure that our sample includes, for example, approximately equal number of men and women, we just sample a certain number of men and we sample a certain number of women, as opposed to sampling a certain number of people and hoping that they'll be approximately the same number of people of different gender. So that's what stratified sampling is about. It has some pleasant properties, except just covering more of the input. Under certain conditions, you get much better accuracy of computing the mean. So this kind of sampling is also used, as far as I know, for Monte Carlo integration to improve its accuracy.
Can you say what sort of assumptions you have to have about the Fs in order that convergence to be true?
Unfortunately, I cannot say which assumptions give you that. I just advise you to read an actual statistics textbook because I don't know enough about this. I would appreciate if someone knew what the assumptions are, but I just don't remember what it is precisely. So, okay, so with stratified sampling, once you divide your input space into a bunch of regions, you can compute variance in two ways. First, you can compute the variance within each region, or you can compute the mean within each region and see how much those means differ. So you can look at the variances within regions, and you can look at the variance between regions. And it turns out that comparing those variances tells you something about whether or not the regions differ. I think this is already starting to make some sense with respect to sensitivity analysis to the factor which region you chose. So, yeah, so if you have a stratified sample, you can compare variances within and between regions. And there are some formulas that can tell you what exactly to do with these variances to tell if the regions are different or not. And there is, so one of the most widely used statistical methods is called ANOVA, analysis of variance, and it's specifically about this. So it's about comparing variances within and between parts of a sample. So for example, you can compare the variances. So for example, you can take a number of patients that have a certain illness and compare the distribution of outcomes for people who received a treatment and people who didn't, or people who received different treatments. And if the variances between and within parts are different, then we can say that which part you chose explains some fraction of the variance. It's a pretty decent measure of sensitivity to a single parameter, though it won't work very well if you have complicated interactions between parameters. But that's the topic of the rest of the talk. Right. So how do we extend this to a space that has a lot of dimensions? And how do we attribute variance to more than one factor? Here's how we do that. So we're going to talk about combinatorial designs. It is a class of experiment designs that have some interesting combinatorial properties with respect to covering a multidimensional input space. So the simplest possible design is the full factorial design. So for example, if you have two parameters and you would like to cover 4 values of each of them, you can just sample 16 points. It can kind of get ugly if you have 1,000 parameters. So we're going to have to ignore some points. For example, we can ignore all the points over here. And now we still sampled 4 values of each of the 2 parameters, but we use 2 times 0 points. So we need to sample only some combinations of all parameters, but we need to have some kind of symmetry. So we need to cover the full range and have some fairness and comprehensiveness. So let us talk about how we can produce interesting designs of this sort. So this is a full factorial design for 3 parameters and 2 levels. Nothing interesting about it, it's exponential. But the thing is that if we take products of these factors, then we get a design with 7 factors that still has some really interesting properties. So first, each column has the same number of high and low levels, and also each combination of 2 columns has the same number of high high, high low, low high, and low low. It is, this design does not have such a pleasant uniformity property if you look at 3 columns, but it is good up to combinations of 2 columns. So it has a remarkable degree of symmetry while being for 7 parameters and using just 8 points for that. So it covers this space of 7 parameters pretty well. Now, there is another class of such designs. It's based on so-called Hadamard matrices. These matrices are produced in the way that you see here on the picture. And this design allows you to produce good quality experiment designs for a number of parameters that's a power of 2. So the thing is, it gives you basically designs that have the same number of any of the 8 possible combinations for any 3 columns. There's a way to make it even better if you stick to a matrix like this and this negation together. Yeah, so you get a design that's uniform on 3 columns. I was mistaken when talking about it on the previous slide. So here you have 4 parameters and 8 points, and any 3 parameters are basically covered uniformly. Now, there is another class of experiment designs called Latent hypercubes. The thing is that, so a latent hypercube is a hypercube where for every row and column and whatever you call it in higher dimensions, you have just a single point. So, for example, here we're seeing 2 latent hypercubes of dimension 2, so latent squares with 4 levels, and so both of the parameters, both of the 2 parameters have 2 levels covered using 4 points. Here's a more interesting example of a latent hypercube. We have 12 points and 9 parameters and 6 levels, and for every parameter we have each of the 6 levels appear twice. So this might kind of seem remarkable, but it actually isn't. So this design is very easy to produce. We just take, so to produce each column, we just take basically an equal number of each level, and we shuffle these columns independently. The problem is that we can get ugly column correlations because we didn't do anything to avoid correlations. So it may turn out that we have explored, for example, only high values of x1 with high values of x4, but we didn't explore what happens if x1 is high but x4 is low. Let's talk about how to do better. To do better, we need something called orthogonal arrays. Yes?
Could you explain what you mean by levels in the previous one?
Yeah, so levels are just different values of a parameter that we're exploring. For example, I don't know, if you're looking at 6 people receiving one of 3 different treatments, you have 3 levels for the factor treatment. Or if you're looking at a quantitative factor, for example, age, you can have, 1 level for people under 18, 1 for 18 to 25, and so on. Okay, so orthogonal arrays are a class of experiment designs that has even more symmetry. So, for example, this is a design for 4 parameters and 3 levels, and each pair of columns has each of the 9 possible combinations. These designs are a lot more remarkable than latent squares and things that we discussed before, but they're pretty difficult to generate, but some algorithms exist to do that. I actually don't know how those algorithms work, but I guess if you ever need an experiment design, you can find it. All right, now just one final point about experiment design. So what if the factors we're looking at are not integers? So how do we choose the levels for a continuous factor in a way that we cover the input space in a representative way if choosing each level the same number of times? The short answer is that you should choose levels corresponding to quantiles of the distribution of the factor. And the design only tells you which quantile to choose. So, okay, now what can we do if we have invented an experiment design? So we created an experiment design and measured the model at every point of it. And what can we do with all those points? We can estimate some statistics of the output. For example, we can measure the mean value of the output over the whole input space, given that we know that the input space is represented fairly well. Or we can compute the variance, or we can compute linear regression on every parameter. And it is, so this way you can compute linear regression on every parameter without doing a separate set of experiments for every parameter. So if you have a model with 20 parameters and you create 1,000 points, you basically get results for linear regression on each of the 20 parameters that are kind of as good as if you just chose 1,000 different points for each of them. So you get a 20x reduction number of points for probably the same accuracy. I'm not sure, but it should be something like that. And another application is that you can use experiment designs as a basis for other sensitivity analysis. Which ones in particular? That's what we're going to talk about. And also, you can use them as a basis for super simple sensitivity analysis, where you just have a factor with 2 levels, and you just compare the mean value of the output at level 1 and at level 2. And if the mean differs a lot, then you say that this factor matters. This obviously doesn't always work very well, but sometimes it does.
Yeah. Can you find what ME is fair?
Yeah, so ME_R means ME is main effect and R is the index of the factor. That's the notation the authors in the book use. I actually don't know what specifically R refers to. Maybe it should better be called F or P, but anyway. Yes.
In the experimental designs that you discussed, the result of an experiment was never used to determine what other experiments you should do.
Questioners, please stand up so everyone can hear the
I'm going to repeat the question. So the question was that in the experiment designs we discussed, they were kind of all static. So we chose points up front and then ran the model on them. And I guess the question is, can we do better if we choose further points based on results on that earlier points? Yes, and this is something that we'll talk about later. So if you have a good way to do this, that's really helpful. So it is a much better way to do experiments if you can use earlier results to choose further points. But I don't know which specific methods can do this, but they're really important. Okay, so let us talk about how we can deal with a lot of parameters. Suppose we have a model with 1,000 parameters, and well, 1,000 parameters cannot all be influential. The influence of 1,000 parameters cannot, so it cannot be that each of them has a degree of influence that's more than 1,000. And a degree of influence of 1,000 is not very big. So they can very well all be non-influential, but they cannot all be influential. So the problem is that if we choose an experiment design for 1,000 parameters and run a model on it, then most of the points we generate will differ by a lot of parameters that are irrelevant. So most of the experiments will change parameters that don't change anything at all, and this seems wasteful. It would be nice if we could just mostly focus on the parameters that are important and change only those. It's kind of a catch-22, of course, but there are some techniques that can help us. So the question is, can we quickly throw away tons of unimportant parameters and focus on the important ones? Yes, we can, and we don't even need as many measurements as we have parameters, and here's why. So there is a famous interview question type of problem where we're trying to find a coin, a fake coin in a set of 12 coins. using only 3 weighings. And well, you don't need to weigh coins 12 times. You can only weigh them 3 times. And the deal is that any particular comparison here, any particular weighting can give you information about many coins at once. So for example, if you took the first 4 coins and the second 4 coins and compared them, and it turns out that their sum is equal, this means that none of these 8 coins is fake. So with just one experiment, you eliminated 8 coins from the picture. In a similar way, it turns out that there are methods where a single result can tell us something about a lot of factors. How exactly does it work? Here's how. So suppose we have a model with 1,000 factors and we try to change 16 factors at once. So for these 16 factors, we invent, for example, 50 possible combinations of these 16 factors. And we treat this combination as a single factor. And we measure the influence of that factor using only 50 measurements, and we see that this factor is actually irrelevant. And then this means that we can throw away all of these 16 parameters. If their combination is irrelevant, then each parameter individually is irrelevant as well. Now, if the combination is relevant, then we have to dig further and see which particular parameters of these 16 cause the combination to matter. So we'll have to subdivide the combination somehow, or maybe we'll have to do something else. Yes?
What about the possibility that 80 factors have a positive influence and 8 have a negative influence and they cancel themselves out, but in fact, all are influential?
So the question is, what if of the 16 factors, 8 have a positive influence and 8 have a negative influence and they cancel out? The answer to that is that if we chose the combination in where the factors are uncorrelated, you probably won't end up with that. So it will be a highly unlikely coincidence that they cancel out. It is possible in principle, but it is not possible on average.
Are you saying all the factors are completely independent? That one of the factors would be 16, that might depend on something else that's outside of the 16.
Yeah, so the question is, am I assuming that factors are independent? Unfortunately, yes, I am. So dealing with dependent factors is apparently an area of active research, and the authors of the book don't give any very good methods for dealing with that, except saying that if one of the factors depends on another, just throw away one of them. So everything that I'm talking about relates to models where factors are independent. If you have a different model, you have to do something to your model, transform it in some way to make sure the factors are independent. But if they are, then these techniques apply. So if you have a lot of factors, if you have n factors, you can allocate them in a number of groups and use some other sensitivity analysis method to see which groups are influential. And then the influential factors are at the intersection of influential groups. So the factors you will get displayed are the factors that are actually influential, plus some false positives, specifically factors that happen to often share a group with any other influential factor, not necessarily the same one. So there will actually be a lot of false positives, and it is difficult to retrieve them. There are some ways to do that. For example, you can randomly invert signs of a parameter in different groupings, and then you can how that will have. So it will have different influence in different groups, and then it will be unlikely that in all of them it will be considered influential. Then another way is to identify some factors that are clearly important. If you see that like a factor, every group where a factor appeared is influential, then it is probably influential. So you can identify some factors that are important, and then you can eliminate their influence. For example, you can do an HDMR and subtract the terms that relate to this factor from the model. and you can start analyzing the rest. Then you're proceeding on a model that depends only on the other factors, and this important factor won't anymore introduce accidental impression of relevance to other factors. And finally, the real killer method is to do grouping in an adaptive way, which means based on some information that you obtained from looking at some of the groups, you decide how exactly you will form the other groups, and this is called combinatorial testing, combinatorial group testing. It is also currently an area of active research, and I don't know what the methods are, but it is much better than just doing grouping blindly. If there is a combinatorial group testing expert in the audience, just please tell what you are and tell us how to do it. It will be really helpful. Okay, so this is how you eliminate a lot of factors, a lot of unimportant factors at once, and how you quickly filter the important ones. Of course, it then still remains to quantify how important they are. Okay, now here's another question. So suppose you generated an experiment design and you ran a model. So for example, you generated a really big orthogonal array that's all neat and symmetric, and you ran a model on its points, and you did some analysis on it. And the analysis said, I don't know, there is not enough points to tell anything with confidence. So what do? You probably don't want to generate another orthogonal array because it's expensive. It means that you have to double the amount of computation just because you had slightly not enough accuracy. So it would be nice to be able to continue the experiment and add just a little more points to it. So we would like to use all existing points and preserve the quality of input coverage, so still have comprehensive and fair coverage, but just add a little more points to it. Neither of the designs we talked about are particularly conducive to that. But there is a class of sampling methods that happens to have this property, and it is called quasi-random sampling. So there is a thing called quasi-random sequences, and here's an example of a quasi-random sequence where each element is a two-dimensional point in the square 0 to 1. And on the left you see the first 10 terms of the sequence, then you have the first 1,000 terms, and then you have the first 10,000 terms. So you see that it has some interesting properties. So it covers all regions of the input pretty fairly in the limit, much better than simple random sampling would do. But also it is incremental. You obviously see some patterns here, but maybe you can hope that they don't particularly correlate with the patterns of the shape of your function. If they don't, then you got what we're looking for. So we have a method to continue an experiment and to generate more points while preserving fairness and comprehensiveness of coverage of the input space. And these sequences are also called low discrepancy sequences, where discrepancy basically means something like the distance from the largest possible distance from an uncovered point to a covered point. And there's a bunch of algorithms for generating them. They're quite neat, and for example, some of them are based on reversing the digit representation of numbers between 0 and 1 under a sum base. So yeah. Now for something completely different. So we talked about one-at-a-time designs, and we talked about designs that give us multiple points per parameter. So one-at-a-time designs are good because they allow us to isolate the influence of any particular parameter. And the other designs, like latent squares and orthogonal arrays, allow us to use few points to cover a lot of input. It turns out that we can combine them and get something that's called the elementary effects method. Here's what's an elementary effect. If you have two neighboring points, Then the elementary effect is something that looks like a derivative between them. So we take the difference of the output and divide it by the difference in the input. Each such pair of points gives us an elementary effect, which is a single number. And then you can analyze the distribution of these elementary effects. If you sample a lot of elementary effects from the input space, you can look at what was the value of each of these effects. And for example, if it was consistently positive, then it probably means that your factor has a consistent positive influence. Or if it was consistently pretty large, but only by absolute value, then your factor is probably influential, but with different signs in different parts of the input space. Or you can take the variance of these elementary effects with respect to a single parameter, and if the variance is large, this means that the elementary effect is very different depending on where exactly you take it. This means that this parameter interacts with other parameters a lot. I imagine you can also just look at the distribution of these elementary effects and tell something from it, but these are three basic analyses that you can do with it. So now how exactly do we choose these elementary effects? So how do we choose where to sample these pairs of neighboring points? We can use one of the methods that we talked about. So for example, we can plant these pairs of points in points of a Latin square or orthogonal array. But we can actually do still better, so we can also take an orthogonal array or a Latin square and plant little trajectories in them. So here we have two parameters, and we have chosen 4 points using a Latin square. They're drawn in blue over here. And for each point, we do 2 steps, one step at x and one step at y. And so we get something like 8 pairs of neighboring points that tell us something about each of the 2 parameters. So in this case, this is actually not optimal because it was almost like the full factorial design. But if we had a lot more levels, a lot more than 4 levels, then we would still have 8 elementary effects at the cost of well, not many points, at the cost of 12 points. This is better than 16 points, which would be the naive way to sample 8 elementary effects for 2 parameters. Actually, it would be not 16, it would be 32. So we use just 12 points instead of 32. So that's the elementary effects method. You sample elementary effects, which are neighboring points that differ only by 1 coordinate, but you sample them in many portions of the input space, for example, chosen using some other experiment design method. Okay, now let's go to the meat of the talk, which is variance-based sensitivity analysis methods. Here's a function that depends on 4 parameters. It's taken straight from the book that this whole talk is based on. And here we're plotting just a scatter plot of 1,000 runs of the function versus each of the 4 parameters. So if you look at these 4 scatter plots, it's kind of obvious that the 3rd and the 4th parameter are the most influential, because the scatter plot with respect to them has some shape, but there is no visible shape with respect to Z1 and Z2. Now you're probably wondering how the formula of y looks like. So what was the actual function? I'm gonna give you a hint. I'm gonna show you how the derivative of y over each of these 4 variables looks like. Here's how the derivative looks like. So the derivative of y over each of these 4 factors is the same, and it's 1 over the whole input range. So y is actually simply the sum of these 4 factors. And then, well, what the hell? So clearly the dependence is different, but the shape of the function is the same. So it's just a sum of 4 terms. it turns out that Y is more sensitive to Z3 and Z4 because these variables themselves are more uncertain. So if they're more uncertain, then they contribute more to the uncertainty of output. This is probably something to think about. So this emphasizes why uncertainty of inputs is as important as the shape of the function itself for describing the uncertainty of Y with respect to a particular parameter. Yes, there's a question. Sorry?
What if you normalize like Z3 and Z4 before coming in there? Is that just now?
Yeah, so the question is, what if we normalize, normalize Y, normalize the uncertainty of that? Yes, that's exactly what we should do. So when people are analyzing the sensitivity of linear additive models, we're actually not looking at the derivatives, we're looking at derivatives normalized with respect to variance. So we're multiplying the derivative by the variance of the input and dividing by the variance of the output. And this way, inputs that are more variable, we're considering them more sensitive. This is called sigma normalized derivatives. They have a really interesting property. If you take the sum of squares of these sigma normalized derivatives, you get 1. Or in other words, if you multiply all these terms by the variance of Y, this means that the sum of squares of variance of input times derivative is the variance of the output. So you have decomposed the variance of the output into terms that look like derivative times uncertainty of input. So this is a decomposition of uncertainty of the output. This is a decomposition of the variance of the output to terms attributable to each of the different inputs. This only applies to linear models, but we're going to learn how this applies to additive models, which are not necessarily linear, so which can be a sum of nonlinear functions. And then we'll generalize this to models that are not even additive. And that's the really interesting part. So variance-based methods are methods that attribute variance of output to different sources of it, specifically to variance caused by different inputs and different combinations of inputs. These methods have a number of good and bad things about them. So the good thing is that they don't depend in any way on what kind of models you're considering. So they're not even looking at the shape of the function itself. Another pro is that they're global. So these are methods for global sensitivity analysis, and they look at the whole range of inputs. They explicitly account for interactions of inputs, and they don't break down if you have a term like x2 times x3. Yeah, and they allow you to treat several factors as a single group. So what exactly does it mean to treat several factors as a single group? So for example, you're analyzing something about people. And you can say that people have certain biologic factors to them, and some socioeconomic factors to them, and maybe some other factors. And you can, for example, quantify the influence of socioeconomic factors of a person to the probability that they'll break their car this year, as opposed to looking at each individual factor. So this is pretty useful because it allows you to interpret sensitivity in a hierarchical way. Okay, the cons are that these methods are extremely computationally expensive and they require a lot of model runs. This can be improved somewhat with meta modeling, so with approximating the model itself. But anyway, you need a lot of model runs, and I suppose you listen like this. And the other problem is that since they're global, they... What's that? Let me try again. Okay, what do we do? Okay, that gives hope. where's the Chrome? Okay, give me a minute to fix this.
Searching for salts. Okay.
Okay, okay, so as I said, another problem with these methods is that they're inherently global and they cannot tell you that, for example, the parameter x matters, but only if parameter y is high. So you can get answers to these kinds of questions. And I don't know of any methods that help you get answers to these kinds of questions. And that's one of the open questions. Right. So the key concept behind variance-based methods is fraction of variance explained. The point is that if you have variance of the output, you can say that a portion of it is explained by a parameter, and a portion of it is not explained by the parameter, and it is the variance within a particular value of this parameter. So you can decompose the variance of a model to the part explained by the parameter and the part explained by other parameters at a fixed value of that one. One way to quantify this is if we kind of take a non-local limit. So here we have this scatter plot. So we have a scatter plot of a function with respect to a single parameter. And we're slicing the space of the parameter into a number of parts. So we're slicing it into 10 parts. And in each of them, we're computing the mean. And we're also computing the variance. So once we have these means, which are red dots over here, they're not actually on a straight line, but almost because it's a linear model. So we can talk about the variance of means. We can take the variance of these red dots. We can see how much they vary from their mean. And that is variance explained by this parameter. And there is also variance that's not explained by this parameter. And it's given by taking the mean of variances within each of these buckets. It's a pretty remarkable property. So it turns out that the variance of output is represented, can be represented as the sum of variance between means and variance. So variance within buckets and variance between buckets. So total variance is variance of means plus mean of variances. It's called the law of total variance. Now just one more thing. So this thing is called conditional expectation. So it's a function that's basically tells what's the expectation of y given a particular value of x. And the variance explained by factor is given by taking the variance of the function. Okay, so this whole thing is called law of total variance, and it says that the variance of y for any particular parameter or condition x, it can be given by taking the variance of conditional expectation of y over x, which is also called conditional variance, and it is variance explained by x, and variance not explained by x, which is the expected variance within x. And to get the decomposition of variance of output with respect to a lot of parameters, we're going to have to decompose this term further. So for now, we only have a term for parameter x, but what about parameter z, parameter t? So maybe we can just decompose the variance into a sum of terms attributable to every parameter. Well, we can sometimes, if the model is additive, not even necessarily linear, we can do that. it turns out that for an additive model, the variance of the output is actually given by taking the sum of conditional variances for every parameter. So variance kind of distributes over the model itself. And then you can have something called a sensitivity index. It's just the ratio of variance explained by the parameter to the total variance, and they add up to 1. So you can say that 30% explained by parameter A and 70 by parameter B, and that's it. In case of linear models, it is actually equal to the sigma normalized derivative. Now, what do we do if the model is not linear? So how will this formula behave if the model is not linear? It turns out that if the model is not additive, if the model is not additive, we'll see that the sensitivity indices, so the fraction of variance explained by every parameter, does not adopt to 1. It adopts to less than 1. So the model behaves as if it was insensitive to any factor in particular. So whenever basically this means that if you look at the scatter plot of output against any particular input, you just see a cloud of points with no discernible shape. And this is because the model depends on particular combinations of inputs. So for example, it depends on, it's high when both x1 and x2 are high. But if you look at dependence against x1 and dependence against x2, you don't see any particular shape. So in this case, the sensitivity indices will adopt to less than 1. So this means that there is a part of variance not explained by any factor in particular. And well, what is it explained by? It is explained by combinations of factors, and here the high-dimensional model representation comes into play. So, as you remember, any model can be decomposed into a sum of terms attributable to different subsets of factors. And it turns out that if inputs of the model are independent, then the variance operator distributes over this. This is, I think, really stunning. So this is the most important thing that I learned from the book. So the point is that you can, for any model at all, if the inputs are independent, you can explicitly attribute variance to parts of variance to every input and to every combination of input. There is no ambiguity, you just get an actual hard number. You can say that 30% is explained by input X, and 20% by combination of Z and T, and something, and some more by some other inputs.
So is there, when you feel this thing looks like a Taylor decomposition, Taylor decomposition assume that derivatives exist. Is there something about an assumption of continuity, smoothness, underneath this?
Yeah, so the question is, what assumptions are there to having this kind of decomposition? I don't think there are any particular assumptions here. The only assumption is that inputs have to be independent. And this is not like the Taylor decomposition, because the Taylor decomposition is infinite, and this one is finite.
Truncated Taylor. You do have it. I mean, tell me it's not. Go back a slide.
Okay.
Okay, so this thing above, these are the first and secondary differences, but two terms of Taylor approximated by finite differences.
Mm-hmm. So yes, it also certainly is a decomposition, but the Taylor decomposition has an infinite number of terms.
Right.
Yeah.
Truncated.
This is not truncated.
Three dots.
The 3 dots, there's only 2 to the power number of factors minus something terms there. So the total number of factors that we're summing over is 2 to the power number of parameters.
Right.
It's not infinity.
That's right. So if you have full factors, you have a third order terms, fourth order terms, and so on.
But
Yep.
it's just a combination of different parameters. So you go x1 to the cubic, x2, and plus x1 square, x2 cubic, both equals to that x1, x2. So it's a combination of different inputs of every parameter, every small element.
Yeah, so the point here is that you can actually take all the summoned here and get a precise decomposition that has no residual term, 0. In case of the Taylor decomposition, this is not the case, so there's no divergence to speak of. A Taylor series typically diverges in the sense that higher order terms get ridiculous coefficients and so on. So you cannot talk about the sum of this infinite series, but here there's no infinite series. It's just a decomposition into a finite number of terms, or finite. I'm sorry, I don't know what's the purpose of. Okay. So yeah, this is the most remarkable formula here, and it means that you can explicitly decompose the variance of the output of a model with any number of parameters. And again, in practice, it usually suffices to look at the first and second order terms, sometimes a little bit higher. So the trouble, no, there's no trouble with that yet. We'll talk about what the trouble with that is later. But so if we have computed this decomposition, so we have two indices for every parameter. One of them is first order sensitivity. We divide the first order term of that parameter by the total variance, and it tells us what fraction of variance is explained by just this parameter. So if the only thing we knew was this parameter, how much could we say about the output? And there's a second type of sensitivity index. It's called the total sensitivity index. It's given if we take the sum of all terms that include this parameter. Or in other words, it's given if we throw away all terms that don't include this parameter at all. So the total sensitivity index tells us what fraction of variance cannot be explained by ignoring this parameter. It is not the same as what can be explained by taking just this parameter, but it is also important. So if the total sensitivity is 0, this means that we can ignore this parameter completely and throw it out of the model. If the first order sensitivity is 0, that doesn't mean very much. That only means that if we only know this parameter, it doesn't help us. But if total sensitivity is 0, it means that if we know this parameter, it doesn't help us because it's completely irrelevant. Okay. So, as I said, the good things about this is that this, so taking this decomposition does not depend on what kind of model we have, on any of its properties, except that the inputs have to be independent. It's global. It doesn't talk about any particular regions of the input space. It explicitly accounts for combinations of factors, short-code interactions, and it allows you to talk about sensitivity with respect to a group of factors, which is basically taken by looking at the terms that consist only of terms in that group. So their grouping factors is achieved by just mapping all factor indices into the group. Now the bad part is that it's difficult to compute. So how do you compute a term like that? How do you compute the conditional variance of your output with respect to, for example, inputs x, y, 2, and 3? Conditional variance, to remind, is the variance of conditional mean. So you have to take a lot of conditional means of y and different combinations of x, y, and 2, and 3. To compute each of those conditional means, you have to look at a lot of values of other factors. So for example, you fix that x1 equals 42, x2 equals 37, and x3 equals 99. And you do a Monte Carlo simulation over the values of the remaining parameters to see what's the expected value of y at this combination of x1, 2, and 3. And you get just a single data point for the outer loop. You get a single conditional mean. And you have to repeat this a lot of times for other points in the space of x1, 2, and 3. And then you take the variance of that and you got a single term of the decomposition.
So what if xi is a real number? And you got to have infinite got very many examples for every fixed xi.
Yeah, so the question is, what if the factors are real numbers? That's not a problem. We'll just sample from the distribution of the factor. So here we're not relying anywhere on the factors being integers. The definition of what is a conditional mean or conditional variance do not depend on the factors being integers. So each of these Monte Carlo loops just requires sampling points. It doesn't require them to be integers. Okay, so the trouble with this is that we need like n squared runs to get accuracy that only improves as order of 1 over n, which is not very good. There are some methods to estimate first and total order sensitivity indices pretty well. Here's one of these methods. So the idea is that you create two matrices A and B. So you have k parameters, k is on the x-axis over here, and you generate n points in the space of k parameters 2 times. And so you get basically 2 n points. You call the first n of these points A, and you call the second n of these points B. These are 2 independent samples of points in the k parameter space. And you mix them in different ways. So for any parameter index I, you can form a matrix C where you take the first sample and you substitute the value of parameter I from the second sample, but you leave all other parameters intact. So this way you get a number of matrices C. And then you compute these scary formulas. So let me tell you about what exactly these formulas mean. So you can compute the first order sensitivity index. So you can compute sensitivity of parameter I of this one. You can compute the sensitivity of parameter I, which is conditional variance of over this parameter over the total variance using this formula. And I'm not going to explain how it fully works, but the point is that this term, the dot product of output of the model on each row of this matrix and each row of this matrix. So if we run the model on every point here and on every point here, where remember every row is a point, we get 2 vectors, each of size n, so we get n results here and n results here. And if we basically take their covariation, we get the covariation between the output of the model on x and the output of the model on x if we change the parameter number I. So we see how much similarity is preserved if we change parameter I. And this gives us the first order sensitivity over parameter I. And the second part here is vice versa. We compare outputs, so we take the covariance of outputs on matrix B and matrix C. And the way they relate is that only parameter I is preserved. So we see how much changes if everything changes except parameter I. If nothing changes, then means that parameter I is relevant. So yeah, this is a really neat method. I don't know how it works fully, but I was able to understand what at least these 2 terms mean. And I hope this gives some insight into the method. Okay, there is also a really clever method for computing sensitivity with respect to multiple parameters called Fourier amplitude sensitivity test. The point is that we sample different parameters at different frequencies that are incommensurate, which means that their ratio is not a rational number. And then we analyze the spectrum of that. And it turns out that if a parameter matters, then there will be a spike on the spectrum corresponding to the frequency with which we vary that parameter. So this method is efficient. It requires a lot fewer points than this method, for example, to compute the first order sensitivity, but unfortunately it can only compute first order sensitivity. Okay, so this concludes the methods, and we're getting to the final part of the talk. So let's talk about what we learned. So we learned what global sensitivity analysis is all about. We learned about decomposing models in an additive way into terms attributable to different subsets of the parameters. Then we're talking about how to extract a lot of information from a small number of data points. This is an area called experiment design, and we were talking about different kinds of neat and symmetric designs like orthogonal arrays and latent squares, and the general concept of stratification, where if you want a certain number of input regions to be covered, then you just sample within these regions explicitly. And we learned about quasi-random sequences, which allow us to continue and experiment incrementally while still having the neat properties of orthogonal arrays and things like that. We discussed the group sampling techniques, which allow to quickly filter out a lot of unimportant parameters in a way similar to how fake coin detection works in a small number of weightings. And indeed, the really good way to do that is to employ combinatorial group testing methods, but I don't know what they are. I would appreciate if someone taught me. Then we talked about elementary effects method, which combines one at a time. We combines the ease of analysis of one at a time designs and the quality of input coverage of the other methods. And finally, we were talking about variance decomposition, where we can decompose the variance of output into additive terms attributable to each individual factor and their combinations, and two ways to characterize the sensitivity of a single parameter. One is first order sensitivity, which is how much can we tell if we just know this parameter, and total sensitivity, which is how much do we lose if we don't know the value of this parameter. If we lose nothing, then it doesn't matter at all. I mentioned factor mapping as one more application of global sensitivity analysis, which is where the output is primary and we're trying to decide which factors matter for whether or not we get a good or bad output. But I didn't have space for it here. So look in the book if you're interested. Okay, now one more topic is what applications can I imagine for a company like Google? This is just complete speculation. This is just areas that I know Google is working in and how I imagine techniques like that could be applied. So I imagine, for example, if you're making a cloud storage engine, then you will probably be interested in what factors cause SLA violations. So what factors cause latency spikes? For example, is it because people are trying to download big files, or is it because they're trying to access this from a remote data center? Or is it because they're using an old version of your API? Or, I don't know, something else. So once you identify the factors that are important in influencing your latency, you can try to focus on doing something about those factors specifically, because you know that if you work on those factors, it will actually change the output. Then there's my original motivation. I was interested in determining which factors influence performance of MapReduce jobs the most. I didn't get anywhere with that, but maybe someone else will. Then I imagine that some advertising product could be interested in knowing what needs to be measured about the user to predict their click-through rate for a particular ad. So if you're writing an advertising product, then there's a number of things that you know about the user and a number of things that you don't, but probably can measure. If you really show the user enough ads that vary different aspects of that. But obviously there is a cost to that. So each ad shown is another possibly more relevant and not shown. So I imagine you could use global sensitivity analysis to know which factors you need to focus on in measurement to as quickly as possible converge on the best possible result. And one final application I have in mind is that it again relates to performance of data processing jobs. So for example, I developed some exciting new feature for map reviews that's supposed to make some jobs go faster. And I'm enabling it, and I want to know if it actually changes anything. So I of course have some benchmarks of my own where the feature is shining and making them faster, but there are all kinds of different jobs running. So people are running extremely diverse workloads, and I would like to know if the feature is having any effect across the fleet and not just in my personal benchmarks. Maybe it's helping some jobs and hurting others, or maybe it doesn't matter at all. Yeah, and then there's a few questions that I don't know the answers to, but would like to know. So one is, what if we have, so all of the methods we discussed, we're talking about, we're assuming that we can run a model at any arbitrary point, just to get data about that point. But there's a different setting where we already have a data set and we have to do something about that data set. The problem is that data sets we have typically have very much dependent inputs. For example, if we look at the data set of MapReduce job performance, we're looking at something that's like as dependent as it can get. So we're looking at the results of people trying to optimize their jobs, trying to find combinations that give them the best possible performance. Obviously, for example, such factors as number of machines used and input size processed are not independent. So people would probably choose more machines for bigger inputs. I don't know how to do it. I emailed the authors of the book and they emailed me some papers that deal with dependent inputs and sensitivity analysis on existing data, but I didn't have time to read them yet. But if anyone is interested, I can just publish pointers to the paper somewhere, maybe just at the end of this slide. Now, another type of question. So, another type of question that bugged me. Suppose we have a certain statistic about the data set. For example, we have the average, average latency, or average something else, or we have the variance of latency. And I'd like to know where this variance comes from. So if the variance of latency is 5, what does that tell me? That doesn't tell me that, so maybe it's 5 because there's one latency spike where it was extremely high. Oh, I think I'm running out of time. Yeah, I just need like a minute more. So it would be interesting to have a way to quantify which, to answer the question, why is the statistics 5? Which points are responsible for it? And for example, look at the points that are most responsible and see if these points are in any way representative of what I'm trying to analyze. And one final question is what to do if the input space has regions which have different sensitivity to a parameter. For example, what if parameter x matters at high levels of y, but it doesn't matter at low levels of y? I don't know of any methods that deal with this, but I think it's really important. So that's it basically. Really good, it's really fun. It's practical and it doesn't require a lot of math. I was able to understand it even though I lost statistics in the university like 8 years ago. So I think you'll like it too. That's it. Thanks. I don't have a citation, but if you Google for global sensitivity analysis, you'll find it. There's no other book called like that. Yes?
When I look and see, I notice there's something that's in some ways conspicuous by its absence. When I think of a lot of experimental methods, as people have done them in fields like biology, for example, you take advantage, it's distinctive how useful it is to take advantage of earlier results to guide your subsequent testing. It's notable by its absence that this does zero of that. If one introduced such methods, does one get a stronger procedure?
So you're talking about the necessity of methods that review existing data. And
No, they use intermediate data to generate it. I do 100 tests, I then take the best point I get out of that, and then I do 100 more related around that. So everything you've got is you basically taking all the data before you do any of the analysis, doing nothing after, and then doing no further testing after the analysis. You're not learning you're learning statically, you're not learning progressively from the data.
Yes, as I said, I think this kind of adaptive choosing of points is really important, and that's what combinatorial group testing is about in case of experiment designs in particular. And I imagine there's a lot of other methods that try to do it too. Yes?
So one thing is about, I think the method based on the decomposition of variance is very interesting. So could you give us an idea of how long it would take? There would be 1,000 parameters. And the other thing is that, basically it's about how to decide which of the parameters are more important than others based on measurements. Like say there are, is it possible that two unimportant parameters, their combinations are important to give the measurements? How do you decide whether they're important or not?
Okay, so can you quickly repeat the first question again?
It's about the speed.
Yeah, so yeah, you're asking how long it would take to do variance-based state analysis with 1,000 parameters. I imagine the first step in analyzing more than 1,000 parameters would be to use group sampling techniques to throw away the unimportant ones. So it is almost entirely determined by how many parameters you have left after that. Once you have done that, so this technique can help you analyze first and second order sensitivity with at least non-exponential number of points. So you choose a number of points n, and you get a result with accuracy that's, I don't remember exactly, but it's something like polynomial in n. It's not very good, but at least it decreases with n in a consistent way. And it's not exponential. For the exact accuracy guarantees, you'll have to read the papers about it.
And the second one is about if the measurement says that two of the combination of two parameters are very important, but when you calculate the importance of every single parameter is unimportant. So how do you conclude whether they are important?
So the question is, what if you have two parameters that are individually unimportant, but their combination is important? Well, that's exactly what variance-based sensitivity will discover. So when looking at, okay, I probably don't have a slide for it specifically. Yeah, so if we look at this group, which is just an inefficient way of doing that, but it's conceptually the same. So we will get really small term for each individual parameter, but we get a high value if we interpret the combination of parameters as xi. So we will take every possible value of the combination of these two parameters. So here we will look over x1 and x2, and here we will look over all the other x's. And we will get for any particular combination of these two parameters, we will get a lot of points for the other parameters, and we will compute how much does the output vary within this particular combination. And then for other values of the combination, we would also compute the same and compute the variance of that.
So you're doing this before you do the parameter elimination, right?
Yes, so here I is not a single parameter, it's a set of parameters. And minus I is like everything except that set. This also applies to this method. So you can treat I as a vector. You can look at a set of columns. Okay, more questions? Okay, thanks everyone.